1.6, infinite sequences. We did infinite series in Math 20. And essentially, the only thing you need from this page is what a sequence is. It's a list of terms. T sub n is the general term. You have your T sub n and your T sub n plus 1, which is the term after the general term. Okay. All right, so if we look at the first example, it's fairly straightforward. It just says, please find the first 5 terms and then graph what it looks like. So we're just going to plug in. We're essentially just doing T sub 1. So we're plugging 1 in. So that's going to be 1/2. T sub 2, 2, 2/3. T sub 3, 3/4. T sub 4, 4/5. And T sub 5, 5/6. Okay, draw the graph of the sequence. So we graph the sequence. Remember the term number. So 1, 2, 3, 4, 5 is like our x value in, okay, 1, 2, 3, 4, 5. And then I'm going to put 1 here. Okay, so T sub 1, we're at 1/2. So it's there, we'll say. T sub 2, we're at 2/3. T sub 3, we're at 3/4. 4/5, and then 5/6, and you're going to see what's happening here. That dot's a little bit off. It's kind of swings up, but it's going to flatten out. It's never going to cross 1. Okay, never. It's going to be 10/11. It's going to be 99/100. It's always going to be 1 less, right? So it's going to be really, really close to 1, but never get to 1. Do you understand that? Now, this is not on the book here, but if I took the limit of that, what do we expect to get then? 1, exactly. The limit of that that's going forever for infinity is 1. Okay, we're going to talk about infinity in a second, but yes, that's the point. Okay, it's approaching 1 but never hits 1. Okay, 1 million over 1,000,001. That's a really close number to 1. Okay, all right. Any questions on that? Straight. So here, limit as n goes to infinity for 1 over n. So what does this mean to you, or what do you think of? Oops, sorry. Well, what does 1 over n look like as a graph? Plug-ins and points. What's 1 over 1? Okay, so there's 1 point. 1 over 2, 1 over 3, 1 over 4, so that thing's doing like that, right? 1/3, 1/4, 1/5, 1/6, 1/7, 1/8. Never going to get 0 though, right? Okay. How about the other direction? What's it going to do? Yeah, it's going to shoot up because what's something smaller than 1? 1/2. What's 1 over 1/2? It's 2. So when it's going the other way, by getting a smaller decimal, it's getting bigger. That's why it goes like this. That's what 1 over n looks like. If you put 1 over x in your calculator, that's what it looks like. Okay? We don't care about what's left on this one, but we do know that if the negatives do the same thing, but down here. Okay? We don't care about those in this one because it wants us to take the limit from where? To positive infinity. So we're trying to find the limit this direction. So by the picture, what would your answer be? 0. That's correct. Okay? It's approaching 0. As I go for infinity, this line is getting closer and closer to 0. That's what it's approaching. Okay? The reason you can think of that, we're going to do this quite a bit, is that when you plug infinity in like the bottom, if the bottom's growing faster than the top, that number's approaching 0. Let me say that again. If the bottom of your fraction is growing faster than the top of your fraction, that means it's getting close to 0. Because that means there are bigger numbers in the bottom, right? If there's bigger numbers in the bottom, it's a smaller number, right? 1 over 10, 1 over 30, 1 over 100. Those are really small, getting close to 0. Okay? So if your bottom's going faster than the top, you'll get 0. You'll see that a lot in this course in terms of us doing that kind of stuff, okay? All right, so how about this one? Okay, hold on a second. Hold up 1 second. I didn't put a red box in here. Just a sec. Box I didn't put in here. We actually have this definition in Math 20. Sorry, I didn't put it on here for whatever reason. Actually, not this one. Limit as n goes to infinity for 1 over n, and it has an italic there, is always equal to 0 if r is greater than 0. Sorry, that's not an italic, that's an r. Okay. So what that means is that it doesn't matter if it's an n squared and n cubed, it's all. All right, so then example 3, try that one. What do you think that one's approaching? N squared minus n over 2n squared plus 1. Can you see right off the bat if one's growing faster than the other? Nikita, what do you think? Just a little bit, because why? The 2, right? So he sees that n squareds are my biggest, right? They're growing the fastest. This one has a 2, this one has a 1. So slightly bigger, but not exponentially bigger. Okay? Think about that when you think about what that limit is. Okay? See what you can do there. Try to factor it, see what you can do with it. Okay? Plug in some stuff. Maybe use some limit properties. Really play with it. See if you can get the puzzle figured out here. I'll use limit properties to show you. Okay, so this is what we're going to do. Okay, this is probably something you wouldn't think to do off the bat, and that's okay. You're going to see why we're going to do this. We're going to divide everything, the top and the bottom, by n squared, because that's the highest power. Okay? So we're going to do this here. Like that. I'm going to divide them both by n squared. We can do whatever we want, as long as we do it at the top and the bottom. So when we do that, it helps us kind of makes things a little bit easier to see. N squared over n squared is 1. N over n squared is 1 over n. 2n squared over n squared is 2. 1 over n squared is 1 over n squared. Now, I'm going to use the limit properties. By limit properties, we technically can do this. We can go like this. Limit as n goes to infinity of 1 minus limit as n goes to infinity of 1 over n all over limit of 2. I'm just writing, it's redundant. I know you think I'm writing a really long problem. I'm just rewriting what we just had with limits in front of each. By limit property, we're allowed to take the limits of things individually. We've talked about that, right? It was in that very big 8 thing that said limit properties. So all I've done is I've taken my limit to there, to there, to there, and to there. Why that helps us is because what is the limit of n infinity to 1? 1. There's no value, right? It's a constant. That stays 1. We just learned this. What's this one? 0. What's this one? What's this one? 0. We're done. It's 1/2. Okay, if you want the little Cliff Notes version, you take the stuff the highest degree. That's a 1, that's a 2. That's why we got 1/2. These are both n squareds. A 1 n squared over a 2 n squared. That was our limit. 1/2. Yep. Yep, that's the definition we just learned. The bottom's growing faster than the top. Yeah, because that's a bigger than 1, right? A 2 works. If it's a 3, if it's a 4, it'd also be 0. Yep. Anything else there? Okay. So now we're going to do the next ones. We're going to see if these actually exist here. So find the following limits if they exist. limit as n goes to infinity of -1 to the n. So just think about what that picture looked like. -1 to the n. We had a couple sequence series like this in Math 20. What do they do when they have a negative? They bounce. They go positive, negative, positive, negative, positive, negative, positive, negative. So if you're doing that, does that have a limit? Does that have a limit? It does not. Okay? It's not approaching anything. It's just bouncing back and forth. It's consistently different. Okay? So I'm telling you is if you're lost, -1 to the 1 is -1. -1 squared is 1. -1 cubed is -1. Just keeps doing this over and over. It's not approaching anything. It's just bouncing from 1 to -1 over and over. So it's not approaching anything, so the limit does not exist. That's a D&E. Does that make logical sense, hopefully? Okay, then how about 1/2 to the n? This is where I kind of like this one, because to me, if you're good with your fractions, it makes sense. 1/2 to the 1 is 1/2. 1/2 squared is what? 1/2 cubed is what? Keeps getting what then? It's never going to get to what? But it's going to be approaching that. So that's 0. This one, it's going to be 0. Okay. Okay, so I'll write out here for you if you want. So it's essentially this, right? By exponent rules, we can write it like this, right? We can write limit as n goes to infinity of 1 to the n over 2 to the n. We don't have to have 1 to the n. That doesn't mean anything. It's that, essentially. It's 1 over 2 something, 2 to the power. So that 2 is the thing that's growing. The 1 stays a 1. So it's going to get bigger. Yep.
So is it kind of like the example from above from that one to 0?
Right. Right, because the 1 didn't change, right? And so the bottom kept getting bigger and the 1 just held. Because 1 to any power is 1. Yeah, so it is like the one I just showed you, the 1 over n.
What if you had like a different fraction, like that wasn't 1 on top?
That's the definition. You ready? You actually probably know this definition. So when do you think the limit will be 0? What's the definition? Pretty much what Josie just asked. She's like, what if it's a different fraction? When was it convergent versus divergent in Math 20? So think about it, right? Mathematical terms. What does convergent mean? It's converging to something. So it's in your mind, would you say if convergent or divergent has a limit? Convergent, just by definition, right? If it's converging, it's coming down upon something and it's getting really close to it. So that's the limit. If it's divergent, it doesn't have a limit, it's just taken off. Okay? For us, we call that infinity. Okay? But my point is, this is what causes that. When r is between 0 and 1, it's going to have a limit of 0. When your r is between n and 1, so by r they mean this guy, the 1/2 there. Here, let me write that. In this definition, that's what r is. 1/2 is the r. If that r is between 0 and 1, but can't be 0 and 1, it'll converge to 0 for its limit. That makes sense, because what are numbers between 0 and 1? 2/3, 3/4, 4/5. All those numbers, the bottom is what? It's bigger. So if the bottom's bigger, you're going to 0. That's what this is telling you. Okay? I might have had that box on there. Yeah, so here it is better if you don't like my handwriting, which makes sense. Okay, that's what I just wrote. So if r is less than 1, okay, so that's just counting for the negatives as well. So that means essentially between -1 and 1. So all fractions between -1 and 1. Same thing as Math 20. Those will be convergent. Those limits will be 0. I'll pause it, see if you have questions. Look of it. All right, so the Fibonacci sequence defined by recursively by the equations f of 1 equals 1, f of 2 equals 1, f of n equals f of n minus 1 plus f of n minus 2. So it's kind of that weird, it's 1, 1, it goes 1, 1, 2. So it's adding upon the previous. 1 plus 1 is 2, 3, 5, 8, 13, 21. That's Fibonacci sequence. Okay? And what they're saying by definition here is you're adding up the previous terms to each other. But that starts at n greater than 3. Okay? So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 5 plus 8 is 11. Or 13, I mean. And 13 plus 8 is 21. That's what the pattern's doing. And so that's just, I'm just introducing the Fibonacci sequence. It builds upon itself. That's what recursive means. Builds upon itself. Okay. Like I want to be short and sweet today, so I'll skip the paradox, but you're welcome to look at that. It's interesting about how you can convince somebody that a hare's or an Achilles is slower than a tortoise. But anyway, we'll stop there.